Check. Can you type a yes if you can hear me? Check. All right, good morning. Good evening. Let's get started. Okay, so technically this could be the last meaningful lectures, and Wednesday, hopefully I can finish everything today, and then Wednesday we can use the time to do a quick review, right? Okay. So we literally just have two theorems left. One is called Divergence theorem, the other one is called Stokes theorem. Very important theorem. If you go into electromagnetic field, inevitably you're going to have to use these two theorems, okay, for your future studies. And also very useful for fluid mechanics, okay, or aerospace applications. So very fundamental skills. Let's do a very quick review. Mainly want to review the curl and divergence. So those are the two things we have covered. Curl, just a quick review here. Curl is mathematically is written as del cross F, or you write it as a curl F. Okay. And we use curl, okay? We use curl to, if we use a curl dot and in hat. So for example, you have a vector field and you pick a point in this vector field, and then you choose the direction, okay, within that vector field. So in hat representing that direction. We typically use a small curve C, okay, around this little point, small point here, in hat perpendicular to this small area, okay, enclosed by curve C. Then the curl F dot in hat give us the so-called circulation density in that in hat direction. Okay, that's curl F. And so curl F give us two informations. The direction give us the maximum circulation, and its magnitude give us the value of the circulation at that point within the vector field. Divergence del dot F, okay, it yields a scalar quantity, not like a curl give you a vector. Right? Divergence yields a scalar quantity. This scalar quantity literally basically means it's called flux density. Right? If you recall the definition of divergence. It gives you a flux density at a certain point within the vector field. What that means basically is that point a source, or is that point a sink? Okay, so if it's a positive, then it functions as a source. It's as if there's something coming out of that point. If it's a negative, then it functions as sink. So stuff is flowing into that point. Right? So that's what basically divergence, the value of divergence really means physically. Okay. The last two theorems, as you're going to see, okay, so although they're a brand new theorem, they're important, but when it comes to the computation or when it comes to the interpretation, you'll see they're actually not new. We already know most of them. So we just have to put them together and then it becomes a new theory. Okay. So let's first take a look at the first one called divergence theorem. So let me write down the definition first, and then let's interpret it together what divergence theorem is all about. If you have a surface S, and it's a closed surface. So it's not just open surface, it's a surface closed like a spherical surface. Whenever it's a closed surface, and it must be bounding certain 3D region. So spherical surface bounds a sphere region. So this is the assumption here. So we need to have an enclosed surface bounding certain region D. Okay. And on top of that, we pick the normal, okay, the vector normal to the surface pointing outward. Okay. So remember, whenever you have a surface, there are always two directions. And if it's a closed surface, then there must be a vector normal to the surface, either pointing outwards or pointing inwards, right? So in this divergent theorem, we need that vector, the normal vector to the surface pointing outwards. So that's kind of important information. And of course, there's a vector field F. So vector field exists in 3D space. It needs to be defined over this region D. Meaning you pick any point within the region D and you plug it into this vector field F, and it will give you back certain numbers, okay, not infinite. If it's infinite, it means it's not defined, right? So that's what define means. And also, this F is differentiable. Over this region D, because you'll see the formulas involve a divergence theorem, involves partial derivative, so it has to be able to take, right, to give you a partial derivative. So that's what differentiable means. Then here's the formula for divergence theorem. The left side, okay, is a surface integral. So we're integrating over this enclosed surface S, integrate as a flux, right? The surface integral as a flux. Okay, so it's basically you get a total flux out of this enclosed surface. And that equal to a triple integral. Integrate over this region D. And what are we integrating? We're integrating del dot F dV. So this is the formula for divergence theorem. Okay, there are two sides. One side is a surface integral, and the other side is a triple integral. Okay, that's about it. Okay, so let's take a look at this formula. Let's interpret this a little bit. Let's go back to the left side here. Okay, so the left side give you essentially, if you look, this is typical flux surface integral, right? Or surface integral as a flux. So what it gives you is, right, it gives you the net flux. The net flux through this surface. Remember, this n hat, right, is normal pointing outwards. So technically, this is the net flux out of this surface S. Okay, so if I had to draw a diagram in here, okay, so surface S is the enclosed surface, and within that space, okay, bounded by the surface S is the region D. Okay. So right now, and then of course you have a vector field exists in the 3D. Okay. So this side calculated the net flux out of surface S. The right side is the key. Okay, the right side. Look at the right side here. First of all, what is the integrand for the right side? Del dot F. What's del dot F? We just review what's del dot F. Huh?
It's curl F.
Flux density, right? So this is basically this part here is flux density. And if I use very language to describe this integral here, so you're integrating flux density over the whole region D enclosed by the S, surface S. Okay? It's like if I use a more acceptable one, you integrate, for example, mass density over a whole volume or over the whole solid object. What do you get? You get a total mass, right? So here you integrate the flux density, okay, over this whole region D. Then according to this, you get net flux, the total flux, which makes perfect sense, right? So you integrate flux density, you get the net flux out of this surface S or out of the total region D. Okay, so that's a perfect actually explanation why this surface integral actually equal to that triple integral, right? So if you have to write it more generically as a lay language, right, you can write it as what I just said, that right? Essentially flux through S is the net amount of something, let's say maybe a fluid, right? Or maybe, whatever, could be just not right fluid or something. So something's represented by the vector field, okay? Leaving this D, okay, per unit volume. Right, so that's basically what the interpretation of this divergent theorem is all about. Okay. So if somebody asks you the net flux out of the surface S, and then you could, instead of calculate this surface integral, you could calculate this triple integral to give you exactly the same result. So that the application divergence theorem often is just like that. So instead of using this surface integral, you calculate using this triple integral to give you the result. So this side here, more often actually maybe result in a simpler or lesser computations. Okay, so let me show you an example. Okay. But before I show you example, you also need to know is that, right, if the surface S, okay, consists of multiple, okay, multiple pieces of surfaces. Okay. So for example, S equal to S1 plus S2. Okay. So not just one single surface. And it's also very common, right? So for example, you may have a surface at bottom as S1, and then you have a surface at the top as S2, okay? Right, so S1 plus S2 together bound a region D. Then not much difference, right? So when you calculate this net flux out of the total surface S, okay, so all you need to do, you need to calculate two separate surface integral, okay, and together that equal to the triple integral the triple integral like this. Right, this is very commonly seen in one of assignments. It was just like that. You might wonder, what's the usefulness at here? For example, right? So you have calculated the surface integral over S1 already, and you also have the results of the divergence theorem based on the triple integral over here. Then you don't need to calculate the surface integral over S2 anymore. You can use this triple integral result minus the surface integral over S1, then you get to the surface integral result over S2. Right? So that's one of the applications. Actually, exactly one of the assignments that you will see that. Okay, so let me show you an example, a couple examples here. Any questions so far regarding divergence theorem? If you look at divergence theorem, it's definitely a new theorem, but all of the computations involved in divergence theorem, nothing's new. Right? So you calculate surface integral, we already done that. You have to decide what kind of surface is it? Spherical, cylinder, or plane, or is it a generic surface? This side here, just divergence, just triple integral, right? Depending on the geometry of the region D, and you decide on your choice of coordinate system, right? And then you pick the coordinate system and find the integral limits, right? Do all of these necessary steps. Okay, so let's take a look at this example. I'll give you a vector field x, y, y, z, and x, z. Here's a vector field. And then this is a very similar example that I presented as a tutorial question. And then you have a cube added here. So the S, surface S, is the 6 sides of the cube. Sitting in the first octant of the XYZ coordinate system. So let's say the cube, just make it a very small cube, unit length of 1 for this cube. Okay, and now you're required to calculate the net flux out of this cube. Or in other words, the net flux out of the total 6 surfaces of this cube. So if you never learned divergence theorem, okay, and your first time looking at this surface integral, okay, then your traditional approach would be, okay, because the cube has 6 surfaces, so then you need to calculate, right, the surface integrals over each one of the surfaces. Okay. And each one of the surfaces in this case is a very simple surface. They are basically one of the special case, because surface is parallel to either XY plane or XZ plane or YZ plane. Right? Then when you choose the integrals, surface integral for each one, you have to choose the n hat, right, for each one of the surface. So for example, if you're dealing with this surface here, then you have to choose your n hat, which will point into the y direction. So the n hat should be j hat, because remember, this is our word, right? If you're choosing the bottom here, then the n hat needs to be negative k hat. Okay, so on and so forth. So all 6 stuff, you have to deal them with separately. After your calculation, you put them together, you add it up, and you get a total net flux. Okay. Now, however, now we learn divergence theorem, and divergence theorem says, now save yourself surface integral. You could do this triple integral right here. Okay, so let's try it. Let's see how does that work. Is that going to actually work simpler or not? So this guy equal to triple integral del dot f dv. So it looks like what I need to do first is to calculate this divergence of the vector field del dot f. Again, this is a formula, so divergence give you a scalar quantity. It's partial m, partial x, partial n, partial y, and partial p, partial z. So this is your m function, this is your n function, this is your p function. So calculate 3 partial derivatives and add them up. So you get y plus z plus x. The result is y, z, x. So now I'm going to plug it into this triple integral out here. So x plus y plus z. And dv, and this is basically now falls down to a very typical standard triple integral question. Okay? And because this is a cube, so I don't think I'm going to choose any other coordinates rather than Cartesian. So you have dx, dy, dz, and it doesn't matter actually the order at here. Because it's a cube, so the integral limits for all of them will be 0 to 1, 0 to 1, 0 to 1. And your limits decided when you do each one of the integrals, okay, separately. There's no trick at all, right? Each from inner integral till the most outside take the integral, so you get 3/2. Okay. So as you can clearly see, right, this triple integral and here compared to that computation involved for calculating surface integral for each 6 sides, much simpler. Okay. So that I think you would rather probably do this triple integral than that surface integral. So let me show you one more example right here. F equal to z k hat, and S is the outside surface of the sphere, your spherical surface. And you're required to calculate the outward flux, meaning n hat is 1/a x, y, z. All right, so whenever you see this kind of question, I mean, I would actually encourage you to try it out. If you use, I think we did probably one of the lecture examples is exactly the same. So you probably don't have to do that. Sorry. This simple surface integral. Now, obviously, I'm not going to calculate the surface integral right here, right? So you should try yourself. If you use surface integral, what would you do? What's the formula involved? Obviously, it's going to be spherical coordinates. Right? What's the n hat? What's dA? And what do you do with x, y, z? Okay, so all this stuff that for a surface integral involving a spherical coordinates. Okay. But we're going to calculate, right? So using divergence theorem. And see if that actually makes things a little easier. So you calculate divergence theorem, basically you need to calculate del dot f first. So that can certainly be calculated maybe offline outside the integral. So you can calculate del dot f. So you get partial m, partial x, partial n, partial y, partial p, partial z as 0. Okay, the good thing is the current vector field has no X and Y component, no I or J component. So your first two terms will be 0, 0. And the last term, partial P over partial Z is 1. So this del dot F or the divergence give you 1. So this triple integral end up just integrated over d dv. And what does this mean? Volume of the region D. And what is the region D? The region D refer to this volume. Basically, region D is the sphere, right? So if you remember your high school formula, you don't even have to calculate what's the volume of a sphere with the radius of A. A 3 over 4 pi o cube, right? Yeah. So of course, if you don't remember this formula, then just apply spherical coordinates and the limits, and you can get exactly the same result. Okay, yeah. Any questions? So you can clearly see the benefit of this divergence theorem. So on the paper, what basically you're being asked is, don't calculate the surface integral, calculate this triple integral. That's pretty much that's it. Okay. Okay, so there's nothing else in terms of divergence theorem. Okay, it's all about integration of flux density is equivalent to getting the total net flux by operating this surface integral. Okay, that's what divergence theory is all about. Okay, last theorem, Stokes theorem. Okay, Stokes theorem. Again, let's write down the Stokes theorem's definition first, and then we'll dive a little bit deeper into the physical meanings of how to better interpret this Stokes theorem. Okay, we'll look at S. Actually, before I talk about Stokes theorem, so let me talk a little bit about the Green theorem here. Okay? So then we can lead into the Stokes theorem. So if you recall the Green theorem, what is the Green theorem? You have a certain region R, okay, enclosed by a curve C in XY plane. Then if you calculate the circulation of the vector field F, so of course F is a 2D vector field, so it's all within the XY plane. It's equivalent to calculate this double integral. As this. And this double integral, sorry, why I'm still writing here. And this double integral, when you calculate out this curl and dot product, it's basically partial n partial x, partial m partial y, dA. Right, that's Green theorem. That's Green theorem. So if you look at the Green theorem here, right? So this side is the total circulation over C. And this side, your integrand is del cross F dot K hat. So first of all, what's del cross F? Go back to the beginning of the review. It's curl, right? And when you use a curl dot, certain direction, in this case, K hat, then you get circulation density in that direction, k hat, right? So what shows up here is basically circulation density, okay? So you're integrating on this right side here, you're integrating circulation density over this whole region R, everywhere within the region R. Here, there's a little bit of circulation density. Here, there's a little bit. Here, there's a little bit. So you're integrating all of them, or you're adding all of them up. Then you get total circulation over this C. Right? That's what Green theorems is all about. Okay, but the Green theorem, the problem is, right, is the C, the curve C, has to be in XY plane. And also a vector field, this is also a 2D vector field. So it's restricted to planar case. So what if my curve C is in a 3D space? Okay, not a planar, it's 3D space. And also this vector field F is not 2D vector, it's a 3D vector. So within a 3D, you have vector field and you have a curve C, okay, somewhere in the 3D space, closed. Then how are we going to do, right? How are we going to get this circulation concept, right? So that's where the Stokes theorem will come into picture. Okay? So basically, what if F is 3D field and C is a 3D curve? Okay, so then what do we do? So now let me write down this Stokes theorem. Okay, so here's Stokes theorem. We're gonna let S, okay, be a very smooth surface, okay, bounded by smooth curve C. Okay. Then, so I'll draw a diagram here to illustrate what this means. So let's say you have a surface, okay, in the 3D space, and this surface is bounded by curve C. So this surface, okay, technically shouldn't be closed surface, because when surface S is closed, guess what happened to the curve C? Topologically speaking, if you have a surface not closed, okay, then you got a boundary, right? So what if the surface becomes closed? Where did that boundary go? Or would you still have a boundary for a closed surface? No, basically if a closed surface, the boundary disappeared, right? There's no boundary, okay? Yeah, so my point is, right, we're dealing with, in this case, we're dealing with an open surface that has a boundary curve C. So this is what's giving it here, all right? Yeah. Then here is the Stokes theorem, okay? Then very probably you are required to calculate the circulation of the vector field over this curve C, right? That's what the circulation of vector field over curve C. And it says it's equivalent to calculate a surface integral. Okay, like this. So Stokes theorem established a connection between the vector line integral and a surface integral. All right. And over this, within this formula added here, the n hat, right, is the unit normal vector, okay, to surface S. Okay. Now what I'm going to write next is very important. The curve C and surface S, they need to be oriented compatibly. Okay. So notice that I haven't drawn a direction along the curve C yet. So you could draw a direction this way, or you could draw a direction this way. Okay. So I didn't draw it yet. I'm waiting for this sentence right here. All right. So the curve C and surface S needs to be oriented compatibly. Okay. So let me explain what this means at here. Okay. Let's explain this first and then go back to the formula and we'll try to interpret this a little bit more here. So first of all, what does orientation of a curve C means? Orientation curve C basically means when you look at from the top on the curve C, so it could be counterclockwise or it could be clockwise, right? So that's circulation. Circulation, you could calculate, say, okay, calculate circulation counterclockwise or calculate it clockwise, right? Yeah. So let's say I choose the curve C as counterclockwise when you look at it from the top, right? So now what I just did is I have picked the orientation of the curve C. Then the sentence says here, surface S needs to be oriented compatible with the surface, with the curve C's orientation. But that basically means you need to pick a direction of n hat, so that n hat's direction needs to be compatible with the curve C. And this compatibility here, right, is to use a so-called right-hand rule. Okay, right-hand rule. So what direction should the n hat be? Should that be pointing outward or should that be actually pointing inwards? Okay, that has to be determined, okay, based on the compatibility with the orientation of the curve C. So how do I nail down this right-hand rule? Okay, so here's a drawing. Maybe I'll just pick it the drawing over here because I won't draw this as good as this. Okay, so this is one here. This is the right-hand rule. Okay. And you can use your finger here to play with this right-hand rule here. First, use your thumb pointing to the direction of the curve C. Okay. So the curve C right now is going this way, right? So you're pointing your thumb pointing to that direction, and then your index finger. So this is where you need a little bit of imagination. Your index finger, try to imagine it's a tangent to the surface S. Okay. And then your middle finger will be the n hat direction. Is that good? Remember, all you need to figure out right now is, are you going to pick the outward direction or inward direction for the n hat? So if you use this finger exercise, apparently the index finger is pointing outwards, right? So you can actually safely see this is your n hat direction for your next step of a surface integral calculation. So the major part is you had to visualize a little bit. Your index finger needs to be tangent to the surface S. Okay, so then you can pick your n hat with the direction of your middle finger. Okay. So for example, this one here, right, is a surface actually pointing down. Right. So try the same thing. Thumb pointing direction of the curve, and then index finger, try to visualize, animate it as if it's a tangent to the surface S, and then the middle finger give you the n hat, right, which is a direction pointing this way. Okay, that's how you choose your n hat and the curve C, and what we call it oriented compatibly. Okay, yeah. All right, so let me give you one more exercise at here and see if you can figure out the n hat's direction. Okay, so let's say I have a cylinder. In the 3D space. Okay. It really doesn't matter how it's oriented, but let's just say I have a cylinder here. And this is the surface. This is the cylindrical surface on the side. Okay, so I'm going to pick the n hat for the cylindrical surface. Okay, so given its surface and n hat, apparently you look at this current surface. What are the boundaries of this surface? In this case, you have two boundaries, right? And one on the top and the other one on the bottom. Okay, you got two boundaries. So let's call this as a C1, the bottom here, let's call it C2. Can you use the right-hand rule to determine the proper orientation for C1 and C2? Meaning, if I look down from the top, should N1 go clockwise, counterclockwise, or should C2 go counterclockwise or clockwise? Your n hat is pointing outwards. Okay, so use your right-hand rule to practice a little bit. So how do I do? Remember, thumb should point to the C1 direction. Index finger should be tangent to the surface, and middle finger should be the n hat direction, right? Okay. So how should I orient the C so that the middle finger is actually pointing outward? So let's do the C1 first. Okay. Should the C1 go counterclockwise or clockwise when you look from the top? Yes, clockwise. Okay. So if you go clockwise, basically means it this way here. So use this the rule we just practiced. Thumb points to the direction of the curve C, and then middle finger, index finger tangent pointing downwards, right? That's how you tangent to the surface. And then middle finger pointing outwards, right? That's basically what n hat is given. Okay. So C1 should be clockwise. Then C2, right? You can do that, will be counterclockwise. So next time, if you're calculating surface integral, right, over this S, okay, so technically you should calculate two vector line integral. One is over C1 and the other is over C2, because there's two boundaries, right, for this particular surface. Okay, very good. Now, another way of trying to interpret this, you could also interpret like using a simplified right-hand rule. Okay, simplified right-hand rule basically means, let's say for example, if a C is pointing this way, it's counterclockwise, and S is this way here. If I pick a point on this surface S here, and then I'm going to draw a little circle, very small circle. Okay, imagine that's a circle, that's a patch, okay, to the surface S. So the n hat, okay, has a right-hand rule, so you can use your right-hand rule to curve up your finger, okay, over these small curves over here, and the thumb is the direction of the n hat. And if you look at the bottom, okay, looking down at the bottom of the little curve, that should be the same flow direction. as the C. Okay, and this n hat, which is the thumb direction, is the right direction. It's called oriented compatibility. Okay. So that's another way to illustrate this. Okay. And as a matter of fact, this leads to the interpretation of the Stokes theorem. And let's go back to the formula here. First of all, okay, again, interpreting this integrand here. So what's this integrand over the right side? Del cross f dot n hat. At the beginning, I just reviewed, when you use a del cross f dot n hat, that gives you a quantity called circulation density. In which direction? In the direction given by the n hat, right? So this gives you a point information. At this point, you got a circulation density. At another point, you have another circulation density. At this location, you have another circulation density. And what are we doing? We're just basically adding up all of the circulation density over this surface S. And what do we get? We get this total circulation over the boundary for this surface S. Right? And if you connect to the Green theorem, and that's basically what Green theorem is doing in 2D. And this is what it's doing in the 3D. Okay, so you calculate the total circulation over curve C, and what the Stokes theorem says is, okay, never mind, you don't need to calculate this, you can calculate this surface integral to give you the same total circulation over the curve C. Now, it seems to be a little more difficult than this one, but in sometimes it's actually proved to be a little simpler, okay? Yeah. So let me show you an example. So f equal to y negative x. Surface is this. Okay. And z is more than 0. So basically half a spherical surface. Okay. And C, okay, is the boundary of the surface S. And this is C at here. So then it's asking you, can you calculate the vector line integral over this curve C? Okay, so obviously I'm not going to calculate this line integral, right? If you do, then you have to parameterize this circle, and then you can calculate the vector line integral as it is. Okay, so you can get it. Okay, but we're going to use Stokes theorem. To use the Stokes theorem, basically we are calculating the right side, the surface integral. Okay. So let's calculate this surface integral here. To calculate the surface integral, you need to calculate the cross product first, or the curl. You got the f, vector f over here. So calculate the cross product, and you got the formulas. So I think you'll be able to get, okay, using the formula, you'll be able to get this cross product, which is negative 2k hat. And the next step, you choose n hat dA, okay, for the surface integral. And because this is a spherical surface centered around the origin, so we're going to choose the spherical surface formula, okay, for the surface integral. So n hat equal to 1 over a, okay, and x, y, z. Now the reason, remember, there's a positive and negative sign. I'm only picking the positive one, is because right now the curve C is oriented, okay, counterclockwise, so the n hat has to be pointing outward. So you choose the positive one for the n hat, and that's equal to 1/3 x, y, z. Right, so the radius of the sphere is 3. And dA, right, for spherical surface, it's a squared sine phi, okay, d phi d theta, which is 9 sine phi d phi d theta. Okay. Okay, so now we're ready to put everything together for this surface integral. So the surface integral del cross f dot n hat dA, so that equal to del cross f is 0, 0, negative 2. N hat is 1/3 xyz. And then dA is 9 sine phi d phi d theta. So let's leave this S for now. So to calculate the star products, negative 2/3 times Z is the result of the dot product, and 9 times sine phi d theta. And you cannot have a mix of Z and phi and theta. You have to get rid of the Z, right? And Z equal to A cosine phi. Right? That's according to the spherical surface. So then you get negative 2/3. A is 3, so cosine phi, and then 9 sine phi d theta. So now everything is in terms of phi and theta. So finally, you can try to find the limits for phi and theta. The limits of phi and theta is based on this surface S over here. So how you find phi? You draw a reading line out of it. This is your phi. So starting from z-axis and sweep across the whole surface. So starting from here is your starting point, and then the other one end up here. So your phi must be from 0 to pi/2. And theta is determined by the shadow of the surface, which is a circle. So got to go from 0 to 2 pi. Right. So that's everything you get. And this is also very simple integral. So you have cosine sine. A simple substitution rule should be able to give you the result. So you should get negative 18 pi as a result of this integral here. So the question basically, is it a simpler calculation than vector line integral or not? It's hard to say, but it does give you an alternative approach to calculate this vector line integral, right? Instead, we're using the surface integral here. So I'm going to show you maybe 1 or 2 more examples of Stokes theorem in the next lecture, and then we can finish our review. Okay? Yeah. So I'll stop here today. Any questions? All good? Yeah.